talked about in the course is selecting features, right? And you can do the entire project using just linear regression and selecting features. You just have to know the right way to select them. And this is a very common thing on the internet, is how do you deal with highly correlated features? And maybe you had a stats course where you talked about this kind of thing. I will talk about it briefly right now. But should you remove any highly correlated features? And some people think that this is true, and some people think it is false. And the thing is, I would say the answer is false. I would use forward selection or backward selection like we did in class. And the reason is, if you are pre-deciding what to do, then your forward selection will be weaker. It'll have less choices to make. And if you're already doing something where the model can make automatic choices, it will be better to just let the model decide. The same kind of thing is happening with this in this last one. So if you look at single variable regression, almost everybody got this one right. Single variable regression does not take into account interaction between things, and it doesn't take into account things of in the presence of other things. So something like the quality of the house, maybe that is very important, but in the presence of the size of the house, it's even more important. So we talked about this thing in the hard part about linear regression is that there's interactions between things. Like the coefficients can flip from being positive to negative depending on what you put in. So it's really important you try to avoid single variable things as really part of your thing. So this was like a major way people can improve is if they're sort of relying on the single variable things as an important part of their thing, like ordering things by their single variable performance, it will not work correctly. But let's talk about this one. So why is it that highly correlated things, you can't just remove them? I came up with a little example that I've used before for this kind of thing. So it's a little thing where I have one set of x values that are highly correlated. So there's x1, x2, x3, x4, x5, and this is the kind of plot you see online with this kind of thing. You're like, oh, these are highly correlated. So of course, x5 is 100% correlated with itself, but the correlation is 90% between x5 and x4. And sometimes people say, oh, you should just remove those. Like, if x5 and x4 are highly correlated, you should delete them. And sometimes that is a good idea, and sometimes it's a bad idea. And if you just do it without checking, then you will sometimes leave performance on the table. So it is a better idea, instead of trying to do it by hand, to let the model decide. And to illustrate this idea of sometimes it's good and sometimes it's bad, I came up with two different y values. And in one of the y values, you can delete a lot of them, and the other one, you should not delete a lot of them. And so that will kind of show you that looking at the x's on their own without the y values is not a good idea. So if you are sort of pre-selecting some, so I have these two variables. So here's y and x, y1 versus x1, and it's kind of like a nice line. I got some trained data and test data, kind of looks like that. And the y2 looks the same. So if you kind of look at one variable at a time, the y1s and the y2s are sort of indistinguishable. Where they do look completely different is if you kind of have forward variable selection, which is a nice algorithm we talked about in the class. And this is exactly the code we had before. If you do the forward variable selection, you can come up with these nice plots of the number of predictors versus the test RMSE. And you can see that for y1, you only need one predictor. One predictor is the best. 2 predictors is overfitting, 3 predictors overfitting, 4 is overfitting, 5 is overfitting. The best possible thing is 1, but for y2, it is 4. So it goes down for a while and then goes up. So there is no way you can tell which situation you are in just by looking at the x's. So if you ever have in your pre-processing, you're sort of eliminating things without considering the sale price, you're probably making a mistake. And I think this is the biggest place you can improve your performance is anytime you're sort of deleting variables, if you have something where you're deleting variables in the pre-processing and then later on you're also deleting variables, you've deleted variables too many times. So you want to just do it one time. And if you have forward subset selection, then it will do it automatically. Like this will automatically delete variables for you. There's no reason to sort of do it beforehand. So I think it's a cool thing that you can't know until you do the thing. You should not be doing it based on just the x's. I will also tell you why. This is a little preview for later in the course. So later in the course, we're going to look at more regularization methods that beyond subset selection. And we're going to kind of look at them from a mathematical point of view. And we're going to come up with pictures that kind of look like this. What's going on in this picture? This is what I call a loss surface. So this is the x-axes are not data, but they are the parameters in a 2-variable linear regression. So a linear regression where you have to estimate the beta 1 and the beta 2. And the thing we're trying to get is that green thing. So the green thing is what we would like to figure out. And the problem is when the variables are very correlated, the loss surface is this really long valley. And really small mistakes can happen in one direction or the other. So if I create some data, that will be the purple surface. Let me see, where's the create data button? It's over here. So you might remember these from other parts of the course. The green is what we really want. And unfortunately, we don't have the green, we have the purple. And the purple is made from random samples from the data. And when you make random samples from the data, because it's really long in one direction, the actual data that you see tends to move up and down in the long direction of the valley. So you're very close in this direction, but you're very long in this direction. And this means that there's a lot of uncertainty in the individual variables. So if you were saying, what is the value of the beta 1, it's hard to know for sure, because there's so much uncertainty over here. It could be a very large number, it could be a very small number. In the beta 2, it's the same thing. It could be a very large number, it could be a very small number. But the point is, when they're highly correlated, we don't actually care about their individual values. If we're making predictions, we just care about their sum. And this is the difference between sort of a data science class and a stats class. In a stats class, you'll want to have very tight error bounds on any of the individual values, and that is why they do this like pre-selection and like eliminating highly correlated things. For us, we have other methods to deal with it that lead to good predictions, but don't necessarily have low uncertainty in the betas. So we sort of have different goals, and that's why we do things a little differently. If you just find a tutorial online where they say, hey, you should eliminate variables that are highly correlated, it will lower your performance, even though the individual beta values will be more certain. It's not necessarily what we want. And we're going to see methods to fix this later in the course. So later in the course, we're going to learn about this thing called ridge regression and lasso regression, and these fix the jumping around issue a bit. Let me see if I can, just as a preview, turn this on. Oh, what do I have to do? There's a little alpha value somewhere. Here's alpha. If you turn the alpha on, things will jump around less, and you'll get slightly better performance. So these jump around less. We'll see that later in the course. So this is kind of a little preview of what's coming on later in the course. Okay, that was sort of a very quick crash course trying to explain what not to do and why not to do it. Let me also move forward. Was there anything else I wanted to say about the pre-selecting? We're gonna have, so later on we're gonna have more, we're gonna have plots like this about the ridge. That's coming up later in the course. But what else did I want to say? It's all summarized here in chapter 2. Okay, so here are some other exercise 2. Here are some other overall comments. So the biggest thing I've seen is people are being extremely, extremely vague and general in their summaries. So people say things like, I made the appropriate choices. I chose the data according to what was best. The whole point of the summary is for you to tell me what you did. So basically, someone should be able to read those little PDFs and like be able to recreate everything you did. So if you say things like, I made the best choices, it does not tell me at all what you did. If you say things like, if you say really general things like linear regression is a good method for making predictions, like we don't want any of that. We want to know what you did in enough detail that we can sort of recreate what you did without any of the code, just knowing all the important choices you made. So things like, instead of saying, I did some of them with median and some of them with mode, make a nice little table. Say, I did these ones with median, I did these ones with mode. To give you a sort of little baby example of this kind of level of detail, if you remember last class, we were working on the Titanic model. So we had this stuff from the Titanic, and we were saying, this is the data we had. We ran either a logistic regression model or the naive Bayes. I wrote up a little kind of what the executive summary, the very first paragraph, would look like for a potential other project. So this is the kind of thing we're looking for. We're not looking for logistic regression is a method that helps you estimate probabilities. We're saying logistic regression was used to estimate who survived on the Titanic and who did not. Of the many variables, I chose these variables. These are the variables I chose. There's a nice list. So I'm saying these are the variables I looked at. And I have details like, look, I encoded the class of the passenger was either 1, 2, or 3. I chose ordinal encoding, right? That's what that means. So these are the choices that I made on my variables. Of course, you guys have many more variables, so you have to think carefully about how you want to present it, because you don't want to have a list that's hundreds long. You're going to have to summarize it somehow. You say, I chose mode for these ones. I chose median for these ones. I deleted these ones for these reasons. Then you might say something like, I ran a regression with all the variables, and then I did something else to reduce overfitting. Then I tried something else, right? And then I used cross-validation to figure out what was the best. This is the kind of level of detail we want. We don't want logistic regression is used to do the probabilities, right? Look, here's the final result. The best subset I found If you measure it by likelihood, it was 5 variables, but if you measure it according to prediction accuracy, it was 4 variables. So that's what I chose. And then there's a nice comment at the end, which was like, my accuracy was really bad. So this is on the Kaggle website, which is acting like you guys have the leaderboard. This problem has the Kaggle website. And if you look at what I did, I had 75% accuracy, but I would have gotten 76% accurate if I just said all the men died and all the women survived. So it's a nice comment that's showing like I'm thinking about the results here and reporting them and what I think about them. That's the kind of detail we want. We don't want general stuff. Does that make sense in terms of the thing? Okay. All right, what else? What other? Let me say my other things and then I'll open for questions. Yeah, another thing, sometimes people kind of get into the wall of text mode or they don't use paragraphs. It should be structured in sort of good presentation style where you have a paragraph that has one main idea, you illustrate your main idea or talk about it, you can use pictures. I've seen a few that are really successful where they sort of had small figures to the right of their text. So they had text and they had a picture right next to it. That's a really nice way to do it. In terms of actual performance, so almost everybody has great performance. Like 25,000 is a very solid starting place. Once you have gotten sort of your main things working, which I think almost everybody has, the biggest performance improvement is your data pre-processing and thinking carefully about ordinal encoding versus one-hot encoding. This kind of stuff will improve your score from 25,000 downwards. I don't want to tell you a number to go for because that is not the way data science works in real life. So in real life, you will never know what is the minimum possible score. I don't want to say you need to get 20,000, but if you can improve a little bit between your draft and your final submission, that's great. Anything near $20,000 is very, very good. It's possible to get below $20,000 if you use something fancier than linear regression, and that is why I separated the leaderboard into 2 leaderboards now. So one of them is, I said linear regression only, ordinary linear regression, and then I made another one that is ridge regression, lasso, fancy stuff, because I think it's like fair to compare apples to apples and oranges to oranges. Remember, the point of the project is not just to get the minimum possible mean squared error. We want to see your way of thinking and how you chose things. If you chose a fancier model, it actually can be harder to do the project because you have more to explain and you have more choices to explain. A really good example is these things that were popular, ridge regression and lasso, which we will get to in the course later. We have not done yet. People who use those did not explain how they chose the parameters. So the code was doing it automatically for them, and therefore there's like a really important element of what they did that is not explained at all in their summary or in their Python notebook, because the computer is doing it automatically, and that choice really matters onto how you interpret what is going on, and they didn't explain that. So if you choose a fancier model, you sort of have more work to do. You can get a higher score in terms of the root mean squared error, but you're making it harder to explain. So it's sort of like an extra challenge mode. If you want to try one of these, you're making the project harder for yourself, which that can be great if you're up for a challenge. But you can have a perfectly fine project with just regular linear regression. Those are my overall things. I still have only looked at about half of them, so I have a few more to look at tonight. But those are my sort of overall impressions. And you have 1 week to sort of, you can do anything you want, any ideas you have, and change it up before your final submission. Any questions or comments about Project 1 overall? Yeah.
So for the executive summary, so should we keep in mind avoiding using the technical terms?
So in the very first paragraph, it should be sort of understandable to someone else. Yeah. So like a good example. Let's go back to what I wrote. Let's see. Were there a lot of technical terms? Like here's a great example. I said the passenger class. I could have said I used ordinal encoding for the passenger class, but I didn't say that. I said which class the passenger was in as a number, 1, 2, 3, right? So that is a good example of a non-technical way to describe what I'm doing. And that's in your very first paragraph. That's what you can do. Yeah, like another example, some people did this log transformation, and they just said, I did a log transformation, but what does that mean? So you can explain, I did the log of this variable, and why I did it. So this is the kind of thing that we want. Yeah, great question. Yeah, I think there's a lot of room for improvement in those summaries. I know kind of like when you're doing your draft, your first priority is to get it working, and so you spend a lot of time on the code, and then you kind of write the thing at the end. So don't feel bad if you get a lot of comments on your summary that says that there's a lot of room for improvement here. None of the grading happens until the final thing, so you still have lots of time to improve it, and that's the whole point of this stuff, is to kind of learn from your draft. All right. Yeah. Any other questions or comments about the project?
Did you also give the reviews for the project?
Sorry?
Did you also give the reviews for the project?
Yeah, so there'll be a review from me that's like sort of a quickish review, but there's also a really detailed review from the TA, who will have like not long paragraphs about each of the stuff.
4 reviews?
You should get 4 reviews back.
Okay.
Yeah. There's like, because of the way that you're giving out 2, but some people didn't submit it and things, so some people might only have 3. They might have 1 peer and 2.
Yeah.
But our goal is to have a short review from me and a long review from the TA from everybody. That's sort of like an official feedback and then unofficial feedback from your peers as well. Yeah, great question. Anyone else? All right, I'm really looking forward to the final. You guys, I've taught this course for like 3 or 4 years now, and you guys have the best scores. So I don't know what you're doing differently. You have the best scores that I've seen. So normally the scores are quite a bit, like the errors are higher, and then it's like more work to get it down. But some of the explanations I think are like, there's a lot of details that are skipped over. So in previous years they've had worse scores, and then like there's been more work trying to get them to improve. You guys are doing a great job. If you can just explain what you're doing and like all the details, you'll have great projects. Okay, let's move on to the next thing. We're going to go back into classification, which is what we were talking about on the previous class on last Wednesday. Okay, let me see. Did I miss anything else? Yeah. Okay. So you're going to have to submit. Because I made 2 new leaderboards, even if you don't want to make a new submission, you have to resubmit your old one. So you must do a final submission sometime this week, even if nothing has changed in your submission. Okay, let's move on back to classification. Well, let's see where we were in classification. Let's do a little recap of where we were. So, what were we doing? We were working on this. Okay, yeah, we were doing the Bayesian classifiers, and we were trying to compare 2 classifiers. So we had this Titanic problem, and we did it with logistic regression, which is the kind of like standard way people do things to estimate the probabilities. And then we also did it with this naive Bayes, right? And then the naive Bayes was basically saying you can combine categories, so something like age and how much people paid, you can combine those just by pretending they are independent given the class, and multiplying the probabilities. Multiplying the probabilities is the same as adding the log likelihoods. That gives you the log likelihoods, then you use Bayes' theorem. And we came up with this kind of predictor. So we were here. This is a predictor comparing the predictions. 1 means you survived in orange, and blue means we predict that you died in blue. And we have the NB probabilities. Those are the negative binomial predictions. And the LR, the logistic regression probabilities. The predictions of what is the probability you died or survived using the 2 methods. And you can see they're pretty well aligned. So like people who have a high probability in one have a high probability in the other. They're pretty sort of correlated, but they're not perfect, right? They're slightly different. The orange or the blue, the color is the true value. So people who we predicted survived with high probability in either model, we're kind of getting a big cluster of oranges. That's good. Big cluster of blues down here. The hard people to predict are people who have a close to a 50% chance, according to our models, of surviving or not. We don't really know what to do. And so you can see also in the histograms, right, there's a lot of people who died. We predicted that they were quite unlikely to survive. There's a lot of people who survived. We predicted they were quite likely to survive. But there's also this like weird fuzzy spot in the middle. Those are the hard to predict people. And we're doing that. Okay, so that's a recap of last time. Before I say anything else, any questions or comments about classification from last time, or what we're looking at vaguely? All right, so the question we're going to ask now is, which one is better? Is the naive Bayes better in this case, or is the logistic regression better? We want to understand which one is better. And one way you could look at it is you could just say, like, which one got more correct? You could say, what's the accuracy? So you could you could say, let's take a 50%. If you're above 50%, predict that they died, predict they survived. If they're below 50%, predict that they survived, and just count which one has the higher accuracy. So this is one method. So now we're answering the question, which is how to compare different methods. And one way is just the straight up accuracy. So this is method 1. This is kind of the algorithm. Greater than 50% survived. Let's say if you predict a greater than 50% survived, then count it as survived. If less than 50%, let's say the probability of survived, then count as not survived, and then measure the accuracy equals how many we got right. Okay, so that is one way, is to measure the straight up accuracy, just the fraction you got right. And we wrote this, basically we take our probabilities, we turn it into an actual classification, and we just use the accuracy. That's the straight up accuracy. There is a variation on method. I'll call this method 1A. Method 1B, this is we can measure the log likelihood. Measure the log likelihood. And remember, we can write this kind of accuracy as the sum of the indicator function. Have I been using an I for indicator, or let me write a 1, because I like ones. It's the 1 if you get 1 point if you got it right. Let's say got data point I right. And we're going to sum that from I equals 1 to the number of data points, and we're going to divide by the number of data points. So that's the accuracy. You get 1 point if you get it correct. You get 0 points if you get it wrong. And we count how many did you get right. So this is the accuracy. We had this on the board quite a few classes ago now. This is the accuracy. Okay. The other way you can do it is measure the log likelihood. This is the cross entropy loss, aka the cross entropy loss. And in the cross entropy loss, remember, it depends how confident you are. So if you're extremely confident and you get it right, that is different than being sort of, if you say, I think it was close to 50% and you get it right. And the way we measure it is we do the cross entropy loss. So we do 1 over the data points, sum from I equals 1 to the number of data. And we'd say we do yi times the log of p hat. Okay. Okay, let me write it like this. Let's do k sub I, where k sub I is the true class of data point I. So in other words, it's some kind of modified version of the accuracy where instead of getting 1 point or 0 points, you can get a log of p hat points where p hat is your prediction. If you predict everybody is 50% likely to survive or not, then you sort of get a bunch of log 2s over here. I guess this is the negative. This is the log likelihood. I want the negative log likelihood. So let me put a big minus sign here. So that is one way to do it. And it's kind of just a fancier way of doing accuracy. In general, I think accuracy is probably better because it's easier to understand. We got 75% of them right is easier than saying, hey, our log likelihood loss was -2. It's hard to parse. But okay, you'll see both of these things. So this is what I call method 1. Just measure how good you're doing, either by the accuracy or the log likelihood. This is something we've talked about before. And you can do this for the 2 methods and see which one is better. Do I have this somewhere? I do not. I should have put it somewhere, but I didn't. Okay, this is like the very basic way you could do it. And essentially, it's like counting, you count the area to the right on the orange ones, and the area to the left on the blue ones, and you see who has a higher total area. That's like which one you got right more often. Okay. Any questions or comments about the straight up method? This is what we've done before. All right. Can anyone think of a reason why this there's something in here that's like lacking a little bit. There's like a little flexibility we kind of left out by doing it this way. So can anyone think of a way you could improve like this? Or what's the deficiency? Like how could you do something? What could you do other than this? And why? Or why? Let me give you some hints. So we're predicting either you survive or not, and you get 1 point if you're correct. This makes sense when things are symmetric. Like if I was predicting red or blue, and I say it's red when it was actually blue, or I say it was blue when it's actually red, those are both kind of similar mistakes. But sometimes the predictions are very different. And I'll give you an example of that, which is the story, that's not what I want, I want this one. The story of the boy who cried wolf. So I made a little thing here. Pretend you are a shepherd boy. Actually, this is the classic fairy tale of the boy who cried wolf. Who has heard of the story of the boy who cried wolf? Okay, most people. So the boy who cried wolf, you're like a little shepherd boy, and you're trying to predict if there's a wolf or not. Okay, and so you see like a fuzzy animal off in the distance, and you're like, there's something over there that is getting near my sheep. Okay, and you can predict either I think it is a wolf, or I think it's not a wolf. And what is the point of the story is that being wrong about whether or not there is a wolf, it really matters in which direction you're wrong. It is not the same when there is a wolf and you think there's no wolf. That is very different than when there is no wolf and you say there is a wolf. So there is a big asymmetry between the two types of errors. The way we talk about this thing in classification, we use what is called the confusion matrix. The confusion matrix that has all the different outcomes. And the confusion matrix is divided into 4 quadrants. There's true positives, true negatives. Those are when you get it correct. So true means you got it correct. And positive or negative is talking about the label of the thing. So a good example in this situation is we could call wolf positive, and we could call no wolf negative. So positive or negative is just a label that we put on it, and in this case we decided wolf was positive and no wolf was negative. We could have easily flipped it, but this is the way we decided to do it. So a true positive means there really was a wolf there, and we noticed and said, hey, that's a wolf. So that's good. We got it right. So the reality, a wolf was there. The shepherd said, hey, I think there's a wolf there. And what is the outcome? The shepherd tells the village, and the village comes over, and they're like, hey, you saved the village, woo! Okay, so the shepherd is a hero. Great, everyone's happy in this situation. The true negative is the reality is there's no wolf, and the shepherd doesn't say there's a wolf, so nothing happens. And the outcome, everyone is fine, nothing really happens. This is the sort of default. 99 days out of 100, this will happen, and then 1 day out of 100, you'll see the wolf, and then you'll be a hero. But most days, there is no wolf. Okay, those are the true classes. And the interesting thing is, what happens when you get it wrong? And there's a big asymmetry between a false positive and a false negative, right? A false positive, so that false means you got it wrong, positive means you predicted that it was positive. So we predicted it was positive, the shepherd said there is a wolf, but we were wrong. So the reality is there was no wolf, and the boy, as they say, the boy cried wolf. So you said there was a wolf, but there is no wolf. In this situation, the villagers will come over, they'll get their pitchforks and come to rescue you, and they will be a little bit angry. You know, they said the villagers are angry at the shepherd for waking them up. So maybe they were all sleeping, and they're a little bit angry. So, negative outcome. Getting it wrong is always bad. That's a negative outcome. The other type of negative outcome, a false negative, the reality is a wolf is there, and the shepherd said no wolf. In that situation, what is the outcome? Well, then the wolf will come and eat all the sheep and kill the shepherd or whatever because the villagers were not there to help. So very different outcomes. In both situations, you're wrong, but a false positive and a false negative are very different. And this is typically the situation. So in real life, you should not really often, this kind of accuracy does not make sense because this kind of accuracy is counting both mistakes as the same. So if you make a mistake and predict it not survive, or you make a mistake and you predict survive, they both count as the same in either of these formulas. These formulas are completely symmetric between the two different things, whereas in real life, we have nuance, and we want to understand the difference between the false negative and the false positive. So what is the point of all this? The point of all this is when you work on a problem, you have to think about this, and you have to answer a question along the lines of which is worse. Which is worse? Is a false positive worse, or is a false negative worse? And it always depends on the problem. So I'm going to let you guys, I'm going to open up to you in this case of the boy who cried wolf and the examples I've described. Which do you think is worse? Should you do this? Should you do that? Or should you do this? It is up to you. I will let you discuss and think. It is kind of subjective. So I'll give you 2 minutes to chat and decide what you think we should do. Okay. Time is up here. Let's see what you said. So the options I gave you were false positive or worse, so you should make that as small as possible. False negative is worse, so you should make that as small as possible. Or should you balance false positive and the false negative rates? And let's see what people said. Reveal counts. Okay. Here we go. All right. So really big majority on the false negative is worse. As a reminder, the false negative in this situation where we've said wolf is positive and no wolf is negative, a false negative means that you are wrong and you predicted no wolf. When you are wrong and you predict no wolf, that means there really is a wolf and the wolf will come and eat everybody. So false negative is worse. Everyone chose that. Here is the thing. The right answer in this situation is that you should balance the false positive and the false negative rates. And the right answer is always to balance the false positive and the false negative rates. So even if a false negative is much, 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 much worse than a false positive, you still need to balance them. So even though a false negative might be worse, it is not true that you should make the false negative rate as small as possible. It's kind of a counterintuitive thing, and I think a lot of people were tricked by this. It's kind of a thing where if you don't think about it carefully, it's very easy to fall into this line of thinking. Getting eaten by a wolf is the worst thing that can happen. Let's just avoid that. We'll avoid this as much as possible. What is the problem with that? Why is it that this is not the correct answer? I'll let you guys think. Talk to your neighbors for a few minutes and try to figure out what the hell I'm talking about. Why is it that we can't just avoid this? I will let you think for a few minutes, and then I'll take an answer from the audience.
That is not what I put.
people get angry at you. So people wouldn't believe you what you said. What is true positive? The true positive also. It's just like
Okay, let's bring back the class here, and let's discuss. So why is it that this answer that most people selected? I agree with everybody that the false negative is worse, but I do not think you should make the false negative rate as small as possible. What is the intuition? Why this counterintuitive seeming statement that I just made? How could that possibly be true? Anyone have a good explanation of why you can't just make this as unlikely as you want? Yeah.
Because I think the model is underfitted. It just learned how to fit one,
Yes.
not the other one.
Yes. Okay. So you're saying underfitted, which is about this over versus underfitting thing, and I think you have spotted that it's actually this idea. You should make the false negative rate as small as possible is actually extremely easy to do. I can, for every given model, no matter how hard the problem is, it's like telling apart really complicated things, no matter how difficult it is to tell if there's a wolf or not, I can always make the false negative rate not only as small as possible, I can make the false negative rate 0. And there's a very simple way to make the false negative rate 0, which is always predict there is a wolf. You will never be in this situation where you said there is no wolf if you just, every time you, like, anytime anything happens, you're like, that's a wolf. You know? Just eyes closed, wolf, 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 wolf. That false negative rate will be 0. You will never ever say there is no wolf and a real wolf is there because you never ever say there is no wolf. So very simple. So this idea of make the false negative rate as small as possible is mathematically silly because when you make it's very trivial to do. You can make it 0 just by always predicting there is a wolf. And of course, always predicting there is a wolf is not good. Why is this bad? I mean, obviously, if you're not even looking at the wolf and you're just saying wolf, 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 it seems like you're doing something dumb. But why can't we just do that? Let's just always predict there's a wolf. What's the problem? Yeah.
The same one is in the story. Nobody actually bothers to use the model.
Yes, exactly. Very good. So even though, and this is the reason we did the story with the wolf as our example, even though the false positive rate, even though an individual false positive is not as bad as a false negative, doing too many false positives in a row, like doing 100 false positives, could be worse than a false negative. And the moral of the story is that if you do too many false positives, then the villagers will get lazy and they will no longer save you when there is a wolf. And so if you have too many false positives, it actually will affect your true positive outcome, right? So even though one false positive is not as bad as one false negative, if you do this thing of minimizing the rate, the false negative rate, you're going to get a lot of these, and that could be worse than getting one of these. So this is the sort of moral of the story is you should, when you're a child, the moral of the story is don't make stuff up. But when you're in data science class, the moral of the story is you always need to balance the two things. No matter how much worse one is than the other, you cannot just always predict one thing because then you need to balance the two rates. So even if one outcome is worse than the other, you must always balance them. This is worth writing down. Let's write it down. So I think this is the fundamental counterintuitive thing about real life classification. Counterintuitive fact about real life classification. You must always balance the two things. I'm going to call them the FNs, the false negatives, and the FPs. And that really is kind of your job of applying what you did to real life is figuring out this balance between the false negatives and the false positives. So this is the idea. And we're going to say, how are we doing this? What is the right way to do it? So the question you should be asking is not, is a false negative worse than a false positive? But the question you should ask is, how do we find the best balance? How do we find the best balance? Okay, and the best balance does not mean they are equal. You have to also take into account the real life consequences. So a good example in this wolf scenario, you should you don't want to always predict there's a wolf, but you would like to make it so that the villagers and come and be angry at you. That should happen rare enough that the villagers continue to come when there really is a wolf. So maybe like once if once a month you have a false positive, maybe that's okay, and the villagers will like forgive you as long as when there is a wolf you really do see it. But if it's once a day, then that's probably too much. So you got to figure out what can we get away with, and like it really depends on the specific circumstances of what you are doing. We're gonna have this balancing is really the core of project 2. I will maybe say that by the end of the class today. How this is going to come up in project 2. How do we measure this? So this actual thing is taken from Google Developers Crash Course, which I have open over here. And then the nice thing about this is they have a nice little widget over here. So I took this screenshot like 2 years ago, I think. And 2 years ago it was the wolf versus the shepherd. And now Google has switched to making it spam versus not spam, which in my mind is less exciting. So in their example, you are classifying email, and you get an email, and the email you either classify it as spam or not spam. A true positive is a spam email that you correctly classified as spam. A true negative is a not spam email you correctly classified as not spam. But a false positive and a false negative are either mislabeling a real email as spam, or a spam email is misclassified as not spam. So of course, these are slightly asymmetric, but not as asymmetrical as the situation with the wolf. The fun thing is that they give you a little widget to play with. Let's see if can I get it all on one line, or does this have to be on 2 lines? Okay. Let's see, can I make this smaller, hide the navigation? Okay. So this is their little thing. So they have a bunch of different symbols over here that represent 2 different things. The purple X's are supposed to represent spam emails. And the the orange circles represent not spam emails. These are regular spam emails. And they have been arranged on a scale from 0 to 1. What is this scale from 0 to 1? This is your prediction based on the model that you made of the probability that it is either spam or not spam. Remember, this is what we have done up until this point. We have done this kind of thing with the logistic regression or the naive Bayes. We have a prediction between 0 and 1, what we think the actual probability is that it's spam or not spam. And the point of what we're doing now is to say that you can take the prediction we made between 0 and 1. What you have to do is add in a threshold. And a threshold will tell you where to cut it off. The most obvious threshold is 50%. If you think it's more than 50% likely to be spam, then you could classify it as spam. And if you're doing this, you are getting all these purple squares correct. So you've made you've made a true positive for all these. They were spam, and you correctly identified them as spam. But you have a little handful of false positives, where it was actually regular email, but you classified it as spam. So you've made mistakes over here. You've also made mistakes on this side, where there's a couple spam emails that you didn't catch because you thought they were only 30% likely to be spam, so they were classified as not spam. So we've made some amount of true positives and true negatives that are shown over here. We have 40 true positives, 44 true negatives, and we have 7 mistakes of this kind and 8 mistakes of this kind. We have 7 mistakes they were actually negative, and we predicted them that they were positive, so this is a false positive. We made 7 mistakes like that. 1, 2, 3, 4, 5, 6, 7. We made 8 mistakes on the other side. Spam emails that got through our filter. 1, 2, 3, 4, 5, 6, 7, 8. And so this is the confusion matrix for this situation. And the thing is, depending on the situation, you might want to trade off one for the other. Like I said before, you can always predict everything is spam, which would be like this. So if you predict every single email is spam, then your false negative rate is 0. You have never accidentally predicted that a message was not spam when it actually was spam. Your false negative rate is 0. But you've made so many mistakes, you've filtered out all the email, so your false positive rate is really bad. So what you want to do is find a balance that somewhere over here you can change the threshold. So you can maybe you want to have something like this, where now we've got quite a few spam messages, but all the emails that we wanted did make it through. So something like 60% would be a good thing here. So let's write this idea down, which is how do you find the best balance? And this is a related idea of you can tweak you can choose the classification threshold. So in other words, you can decide based on your model what should the cutoff be for predicting it's a wolf or not wolf. Yeah, in the example we gave before with the wolf, this would be something like if I see an animal in the distance, if I think there's a more than 5% chance it's a wolf, then I'll call everybody. And in that way, we're pretty covered. Like we can have this be really low, but we can't make it 0. We can't say if it's any animal at all, I should call the village. It needs to have at least a minimum amount. Otherwise, we'll be calling the village too much. And what that is depends on the circumstances, how many other animals are around, and so on and so on. So this is the big idea: is that you gotta choose the threshold, the classification threshold. You'll notice when I said the thing over here before, that the threshold did appear. This does not have to be greater than 50%, less than 50%. So the real thing we should do in method 2 is choose the threshold according to your needs. Choose the threshold to be the best. And the best depends on exactly what you need. It'll be different for different people with different preferences. How annoyed are you by getting a spam email versus how annoyed are you by an email that you were supposed to get not arriving? This will change the idea of what is the best, right? Okay. So this is a big idea, is that in real life, you can't just make a prediction. You have to make a prediction and also tell me how to use the prediction. And this threshold lets you tune to understand different types of errors you can make. This is like a key part of understanding the uncertainty in your predictor. Your predictor is not perfect, and you have to understand that. That goes into telling people how to use it. Okay, this is a good place to pause for questions. Was the little slider clear? All right. So this brings us back to the question of what is better. Now we can answer the question, maybe what is better between the naive Bayes and the logistic regression. If you want to answer what is better, you could say, let's just measure the accuracy, who had higher accuracy, or you could actually compare the entire matrix, right? You could look at this entire confusion matrix. Where did the confusion matrix go? Of true positive versus false negative versus true negative. And if you look at that, I think I calculated some of those. So these are these little things. So this model, with a threshold of 50%, so I put in a threshold of 50%, and it made 123 errors of one type of false negatives, and it made 55 errors of the other type. That is which one is that? The naive Bayes. I will explain the graph in a minute. Don't look at the graph yet. The graph will be coming up in a second. So I made 123 errors of one type, 55 errors of the other type. This 301 and 235 are ones that I got correct. So that's pretty good. Like out of 600-ish people, I got 500-ish correct, and I have 55 and 123 errors. Whereas the logistic regression has this. It has 72 and 59, right? And in this situation, there were less errors in this corner, but more errors in this corner. And you have to decide, is making an error of predicting somebody survived when they actually died, or predicting that they didn't survive when they actually did survive, are those equal? If they're equal, you would just add them together and compare, but maybe one of them is twice as bad as the other one or something. You can decide how you want to measure it. So that's one way to do it. Okay, the other way you can do it is this funny curve. This curve plots the false positive rate versus the true positive rate. Why is there more than one false positive rate and more than one true positive rate? It's exactly because you can change the threshold. So let's go back to this little idea. You can choose the classification threshold, and this will span, by choosing the threshold, this will span all values between 0% and 100% for the false negative and false positive rates. So 0% false positive is over here, and 100% false negative is over here. This is always predict I'm going to say always predict wolf because I like to think in terms of examples. Versus, you could go to the far other side, would be flipped. False, positive, and 0%. False, negative. I think I might have made a mistake in these labels. This one, I want this one to be never predict wolf. So if you always predict wolf, you will never make a false positive. If you never predict wolf, I think this is wrong. What are the two axes on the ROC curve? Let's go take a look. I always mix these up. So false positive rate versus true positive rate is the one I wanted. Okay, let me fix the thing, and then we will be quite happy. Okay. Okay, so if you always predict wolf, you will never make a mistake where there was a wolf and you said there was no wolf because you were always predicting wolf. But your true positive rate will be 100% because every time there is a wolf, you said there was a wolf. On the far other extreme, if you never ever say there's a wolf, you have the thing flipped. You get a false positive rate of 100% because you always predict no wolf. So when there is a wolf, you are screwed. And your true positive rate is 0% because you never predict wolf. So if there really is a wolf, you're also screwed. So these are both, the point is that these are both bad in different directions. Maybe one is worse than the other, but the best possible thing is somewhere in between. Best possible, somewhere in between. Best possible. But not only is the best possible somewhere in between, you can imagine what would happen for all of these different thresholds. So if you set the threshold to 0%, this is a 0% threshold. This is a 100% threshold. You have all the different things in between. And if you just want one predictor, you can say what is the best possible, find it in between. But you can also cycle through all the possibilities and get a nice curve that is doing all of these. And that is what is this. This is the so-called ROC curve. So the ROC curve has all possible values in between. C curve shows the performance of your model at all possible values of your model at every possible threshold. Okay, and to illustrate this, once again, Google has my back and has made a nice little applet. Let me see if I can find the Google applet. It's this one. So here is the true positive rate and the false positive rate. And again, we have the spam and the not spam and the threshold. But what is added is this little thing down here of the ROC curve. Let's do this nice data set. So in addition to changing the confusion matrix, you see that every time I move this threshold around, we get a different point on this curve. And the curve maps out the whole map from 0, 0 to 100%, 100% from start to finish. So here, this is always predicting one thing. You have a 100% true positive rate and a 100% false positive rate. And then on the other side is a 0%, 0%. These are the two extremes that I said before. And the truth is you want to find some optimal place in between, but you can consider what would happen at all these different things. And that is what this ROC curve is. So this is called the ROC curve. ROC stands for receiver operator characteristics, which is fancy talk for nothing. It doesn't give you any information. I don't know why we got stuck with this name. But it's just called the ROC curve, and that's what people use. And it tells you this kind of cycle of all the possible things your model could get. It occurs to me I must have made a typo here. When I did this, it's not 0%, 0%. It's 100%, 100% to 0%, 0%. So I guess, how do I want to do it? This side is 0, 0. And that's because I made the mistake before. And it's 100%, 100%. So you go from 0, 0, that's the bottom left, to 100, 100. That's the bottom right. Let's see if it's correct now. So there's 0, 0. Oh, okay. The threshold, it's backwards. Okay, let me fix it. 100%. 100%. Always predict wolf. Wait. Which one's always predict wolf? I think I drew the x-axis backwards. This is predict everything is email. This is predict everything is spam. So the threshold. Okay, so I have in my example. I guess let's leave it like this, and then this is backwards. So this is 100% and this is 0%. No, but 0% is okay. No, I think it is correct now. Okay, you know, I'm just gonna stop talking about this, and if there's a mistake, there's a mistake. Okay, so all right, I think you guys are getting the gist of it. Okay, so there you go. That's the ROC curve, and you can kind of measure all the possible performances of your model. Depending on what your data looks like, it will look quite different. So this is a kind of a regular thing, kind of looks like this, where on one side you're at 0, 0, on the other side you're at 100, 100, but then in the middle you sort of are like pretty good on both. But sometimes the data is like this. It's kind of imbalanced, where there's just not many of one class or the other class, and so like a lot of dropping happens near the edges. So there's just not many extra spam emails over here, so changing this doesn't change anything. So this can happen too. And then there's like unseparated data, which is like where this is a lot harder of a data set. No matter what you pick, you're going to make a lot of mistakes one way or the other way. And so in real life, this can happen. This means that you're not doing a great job predicting, whereas in something like this, you can get pretty good predictions. So you can kind of see the difference on the ROC curve.
What do you mean by unseparated?
Yes, okay. So I just mean, so when they're separated, most of the purples are on this side and most of the oranges on this side. So our probability thing is doing a pretty good job of separating the purples from the oranges. Of course, it's not perfect. There's some overlap, but it's mostly good. We've mostly figured out the purples are over here and the oranges are over here. In the unseparated case, it's all mixed. So there's a lot of overlap between the purples and the oranges, which is saying that our predictions are not very good, right? And in this situation, you can see it on the curve. That's the point, is that you can see the difference between these two situations without looking at the data, just by looking at the curve. This curve is a lot better because it's separating them out. You can see you can do good at both values by doing somewhere in the middle, whereas in this curve, it's like a pure trade-off, right? You're very close to this line of the diagonal line. So in fact, in my model, I calculated this, and I also drew this dotted line. This dotted line is just like randomly guessing. So if you always guess one way or always guess the other way, you can always just like flip a coin and guess. That would be the red line. So you want to do better than the red line, and the more up into the corner you are, the better you are doing. So this is the naive Bayes, I think, or this is the logistic regression. There's that curve, and this is how did I plot it? I used this function called dot ROC curve. So everybody knows about this ROC curve, and it is baked into scikit-learn. It will automatically take the predictions, which are probabilities, and do all the possible thresholds and give you this nice curve. Okay, so that's the ROC curve. Okay, great. So this means you're doing a bad job. You can't predict things very well. And when it looks like this, then you're doing a pretty good job. You can predict things a lot better. Your predictor is separating things out a lot more. Okay, there is one last mystery, which is, what is this AUC? What is this AUC? It's the area under the curve. So very good. So this is the last secret piece of knowledge that you know. You have to know ROC curve is the special thing. That is the special curve that I just talked about. And the AUC is another secret word that means area under curve. Means area under curve. Sometimes people say AROC, the area under the ROC curve, or the AUROC. And the idea is more area equals better. More area equals better predictor. Less area equals worse. And 50% is the guessing randomly. 50% area equals guessing randomly. Right? So the curve with the dotted lines over here, this is pure random guessing. This is always guessing one way. This is always guessing the other way. You can achieve this middle point by guessing half the time wolf, half the time not wolf, and that has an area of 50%. This whole square has an area of 1. If your curve can get all the way up to the corner and then all the way over, it'll have an area really close to 1. And the bigger the area is, the better it is in some sense. So this area under the curve is 86% for the logistic regression. And then for the naive Bayes, it is slightly worse, so 83%. So this is saying that for this particular problem, the way I did this, the logistic regression is somehow a little bit better than the naive Bayes. Okay. I think that's all I wanted to say about this ROC curve stuff. Now you know all the secret definitions, and you can compare two models. Questions or comments about any of that? Okay, the reason this is important, and you will care about this a lot, is your project 2 is to do exactly this. Do I have project 2 open? So in your project 2, it is once again a giant data set, same kind of thing as before, training set and test set. These are the information about the columns in your data set. The date the client was quoted, these are quotes for car insurance. And it was actually taken from the cooperators who are here in Guelph. So they gave us a nice data set that has been cleaned of any kind of personal information. And they're like sort of like made up names and stuff. But it's based on a real data set that the cooperators have for actual car insurance quotes. And your job is to predict if the person bought insurance or not. That is called bound. So you're going to take all of these pieces of information, like what the car is being used for, the year of the car, the model, the make, and all this stuff. And you have to predict, did the person buy car insurance or not? I think if I go all the way up to the first page, this is the first page. These are all the different cars. There were quotes on, there were 12 quotes or something on January 4th, 2016. These are the different cars. There's more data about each of these quotes, and you have to predict, did they buy insurance or not? Of course, buying insurance or not, again, just like the wolf, is not symmetric. So if I go to the project information, perhaps it will not let me. Okay, you have to stand by while I log in, which is of course very frustrating. Okay. Well, now what is it doing? Maybe I have it in a different window. Sign into your account. All right, I don't know why it's not working. Well, you know what? We can talk about it next class because of tech difficulties. I don't think you should worry about project 2 right now anyway, because you have project 1 to finish off. The main thing maybe you should know about project 2 is I think the due date for the draft is November 14th. So you still have quite a bit of time. We'll talk about it on Wednesday. I can give you the little details now due to the things not working. And let's finish a little bit early today. Any questions or comments? I'll talk about project 2 at the beginning of Wednesday's class. Yeah.
Yes, sorry, you just mentioned your AUC for the
Yes.
plot. Yeah, you said the header is bigger than the naive base.
Right.
Is that due to your data set, or that should be the usual? So you're saying header is better?
No, yeah, I'm saying LR for this particular problem, the particular way I did it, it turned out better. You should think of it as like a little measuring stick, and depending on the problem and what you did exactly, it can be different. There's one of them is not always better than the other one. If it was ever true that one of them was always better than the other one, we would just never tell you about the other one. So all the things we tell you about in the class are sometimes the best thing. Yeah. It depends on the data set and the details of how you did it. So so it depends on the data set and exactly the choices you made in the pre-processing and all the variables you used, stuff like that. Yeah. Okay. All right. So we'll stop there. We'll see everyone on Wednesday. If you want to ask me a question about the project between now and next week, please come by, or you can ask on the forum as well. And otherwise, good luck. And don't forget to do the review if you haven't done it yet.